I'm Ke-Sun, a third-year PhD student from UCSD, advised by Professor Xinyu Zhang. Today, I will present our work, UltraSE, single-channel speech enhancement using ultrasound. Speech communication is known as one of the most common communication methods for both human-to-human and human-to-computer interaction. Typically, for mobile devices, the speech signals are recorded by the microphone and then used by the user interface. However, when there exists noise sound sources in the environment, the recorded sound will contain both noise and the target speech. Speech separation and enhancement method is proposed here to extract the clean speech of the target user in such scenarios. This kind of task is being considered as the holy grail of speech processing because of its wide usage. The more challenging scenario is that a single microphone is used to record more than one speaker's speech along with background noise. Audio-only methods are hard to resolve such scenarios. Although some advanced deep learning methods show the potential to separate the multiple speaker speech, they still face a very fundamental challenge. In the speech community, they call it label permutation problem. As you can see in this figure, even though the speech separation and the enhancement method trying to separate the speech into two different audio streams, they are still kind of like the microphone itself is still don't know which one is from the target user and which one is from the noise user. Existing work proposed to use the audio-visual method to solve this problem. The basic idea is to correlate the speech signals with the mouse movement in a video to realize the robust speech separation and enhancement. However, the video-based methods still have some limitations. For example, they have to use an additional camera for the speech recording, which has a limited angle view and cannot work well in the bad tuning condition and also quite energy consuming. Our work, UltraSE, proposed to use audio-only method to separate the desired speaker's voice from other speakers and noise. Inspired by the audio-visual method, our basic idea is to use ultrasonic sensing as a complementary modality to capture the desired speaker's articulatory gestures and extract the correlated speech signals from the noisy recordings. Compared to the traditional audio recording, UltraSE will continuously transmit the ultrasound by using the loudspeaker on the mobile devices. When user is speaking, the ultrasound will be modulated by the speaker's articulatory gestures close to the smartphone. As a result, the microphone captures both the audible sound and also the reflected inaudible sound. The key advantage of UltraSE is that this is an audio-only method without any hardware modification. It is really general to any mobile devices with only a single pair of microphone and loudspeaker, like your smartphone, smartwatch, even your earbud. After receiving these two modalities, UltraSE employs a novel DNN framework to capture such correlation and denoise audible sound. It can be considered as a separated block in traditional speech processing pipeline. Next, I will present how we sense the speaker's articulatory gestures. It is hard to use ultrasound to discriminate different articulatory gestures, including your lip, your tongue, your jaw, and your movement, and also your vocal cord vibration, because they are complex and mixed together. Meanwhile, the articulatory gesture are also fast and subtle. Our ultrasound sensing meaning only captures the articulatory gestures with the largest motion from the lip and the jaw, which is typically less than 5 centimeter moving distance and less than 80 centimeters per second speed. In comparison, our ultrasound sensing is really hard to capture the vocal cord vibration, which involves only less than 100 micrometer vibration. The advantage using ultrasound sensing here is that they typically have high resolution, which means traditional 20 kilohertz ultrasound will have a 2 centimeter wavelength. And also, compared to the camera-based method, they have high sampling rate. Camera-based method typically have 30 FPS, but for the audio system, they will have 48 kilohertz. The last advantage here is that we use a single microphone to capture 2 different modalities. So they will automatically have a future alignment because they are captured by the microphone itself. We select the multi-pulse continuous wave as our transmitted signals and use the Doppler shift as the feature in our work because we want to achieve a high time frequency resolution for articulatory gesture sensing. As we know, like previously we discussed, the articulatory gesture is really fast and subtle. So we have to try to achieve a high time frequency resolution. In comparison, although FMCW or FDM-based transmitting signal can capture the channel impulse response or Doppler or range Doppler to characterize your mouse absolute distance information, they cannot clearly capture the detailed articulatory gesture Doppler shift because of relative low sampling rate. Besides, the distance information is not that important in our scenario because we mainly consider the handhold scenario where the distance between the smartphone and the microphone is really stable. After receiving the sound signals, we try to extract the single stream audio from try to extract them to two different modalities. We extract the time frequency domain speech spectrogram for audio and the time frequency domain ultrasound Doppler spectrogram for inaudible sound separately. Although these 2 modalities have different frequency band, we find the 2 mutual interference exist between speech and ultrasound, which cause the ambiguity of the Doppler features. First, as you can see, there may exist some speech harmonics that's introduced by the microphone. Fortunately, we can mitigate this kind of harmonics by directly reducing the volume because the second order term, which is the harmonics amplitude, decrease faster than the first order term, which is the Doppler amplitude. Second, we find when we say some specific formula like this kind of formula, we are always blowing the air, which will try to saturate your microphone. So it will generate a very specific tone there. And we try to harness this as a part of our features to characterize the period of specific formulas. Next, we will introduce our neural network design for UltraSE. We try to integrate ultrasonic sensing information into the state-of-the-art speech enhancement DNN design. Our design mainly have 2 parts. One is for the time frequency domain multimodal amplitude network. Another is for time domain phase network. Existing speech enhancement deep learning methods have shown that using the amplitude of the time frequency spectrogram can achieve better speech enhancement performance than using the phase. We try to add a time frequency ultrasound band here in the state-of-the-art amplitude-based speech enhancement deep neural network, and use a self-attention mechanism to fuse it with the original sound to generate an amplitude mask of the targeted user. And finally, we generate the amplitude enhanced time frequency spectrogram. However, the key problem here is whether this fusion has fully utilized the ultrasound sensing information, and how can we force the multimodal fusion network to understand such multimodal correlation. As a result, we try to propose a discriminator network, which is trying to see whether the ultrasound corresponds to the speech. As you can see here, if the input is the like clean speech and ultrasound feature, it will automatically, they will find that they are in a pair because they all characterize the same target user articulator gestures. However, when it comes with this noisy spectrogram and time frequency ultrasound, the discriminator will find the audio is too noisy. It is not paired with the ultrasound. So we try to use the triplet loss in this discriminator. We are trying to force the ultrasound be close to the clean speech or be away from the noisy speech. As you can see this here, after training, the blue and the green balls represent to the real pair, that is ultrasound and the clean speech, they will be close, while the ultrasound and noisy speech, they will be far away. Here is a visualization of the distance of both real pair and fake pair. And then we try to design a conditional gain-based cross-module training to help us train the model. Our previous introduced time-frequency multi-module amplitude network is considered as a generator here. They are trying to generate the amplitude-enhanced time-frequency spectrogram. And then we will try to compare this time-frequency enhanced spectrogram with the ultrasound. So the discriminator, we are trying to discriminate these two. If the enhanced speech is not that close to the ultrasound as a pair, they will feel, oh, this one is not enough. Please try another better generator. So we will do a backpropagation training here to train the generator. Now we only consider the amplitude of the speech spectrogram in our previous design. The reason why we do not consider the phase in the beginning is because in the time frequency spectrogram, most of the phase information is useless and random because their amplitude is really low. However, we find that when the speech signals are significantly noisy, the phase of the spectrogram will be significantly distorted. If we do not consider the phase, although the speech intelligibility is still high, which means you can understand that kind of speech, the speech quality will be low, which means that people will feel kind of uncomfortable and realize some jitter effect when they listen to this speech. So after the time frequency domain amplitude speech, we try to convert the speech back to the time domain and try to fine-tune the phase of the speech in the time domain. We find that learning the phase information in the time frequency domain is extremely hard, but learning it in the time domain will be kind of easy. We design an encoder-decoder-based network to correct the phase of the enhanced speech to improve the speech quality. Then we go to the data collection. Traditional speech data set only contain the raw speech without any ultrasound sensing information. So to evaluate the UltraSE, we have to create a new data set called UltraSpeech, which comprises both. We recruited 20 fluent English speakers to collect the UltraSpeech data set. Each participant was asked to say at least 300 sentences in the speech recognition corpus by using two typically phone holding style, like the phone call and towards microphone style. Note that we only need to collect this kind of clean speech set with the ultrasound sensing information. For the noisy speech part, we can directly use the large-scale speech and some noisy source from existing large-scale data set to build a large-scale data set for us. For example, we use the Libre speech data set and Google Audio set data set as the noisy speech data set and noisy environment data set. So finally, our data set can achieve more than 300 hours state in total. We compare UltraSE with some state-of-the-art speech enhancement method in different scenarios. As you can see in this table, in the first column environment, the S means how many users in this environment, and the A means whether they have some environmental noise there. We can see that the UltraSE outperformed this method in different scenarios, even there are 3 users with additional environment noise. We also test a very challenging scenario, which means that there are 2 same voices in the environment, which means you are saying something with yourself to try to make it much general. And we also find this will only a little bit degrade the performance. We try to do an ablation study here, try to show the design component the usage of the UltraSE, we find that ultrasound will significantly improve the performance of speech enhancement. And with our conditional gain design, it will force the network to learn the correlation between the ultrasound and speech. And finally, our time domain phase fine-tuning will try to bring the speech quality to the next level. And we also try to evaluate the generalization for different holding styles and different environments. We find that UltraSE will always output the case without UltraSE in different holding styles, because even without the ultrasound sensing, it just degrades to an audio-only speech enhancement. And UltraSE is unaffected by the motion artifacts in daily scenarios. We also evaluate it in different kind of environment, like in the bathroom, living room, indoor conference, and outdoor roadside environment. So in conclusion, we try to make a noise design choice for using ultrasound to assist the speech processing. And we are trying to design a multi-module, multi-domain DN framework for single-channel speech enhancement. Our designed conditional gain-based cross-model training can be used in different kind of multimodal denoising. It's not only limited to the speech and ultrasound-based denoising. And finally, we feel UltraSE points to a novel direction that fuse wireless signals to tackle the challenge in traditional speech processing community. And also many companies like Amazon is really interested in this kind of work because they can try to combine their ultrasound sensor in their device to achieve better speech processing. Thank you, that's all.